we are at the first place we are taking our q to be up to x to epsilon, and our theta is something smaller than 1 over x to epsilon in that case, but just for simplicity let's assume that our q is 1 and our theta is 1 over x to epsilon, and let's for simplicity assume that our h is x to 2 over 7 plus 2 epsilon, which is something worse than the theorem I was claiming, but it's much simpler to deal with this case. 2 over 7, so to give you some idea, I just will stick into proving this bigger result instead of doing the whole thing. Okay, and then we have to bound this guy up here. Okay, if we take, okay, let's remove this and going to bounding this. So if we take q equal to 1, we can forget about this, we can forget about this. And if we take theta to be x to minus epsilon, we have here x to 1 minus epsilon, and we have here, okay, so let's write h1 theta h. So we have here h1, and here we have t minus h1, t plus h1, and here we have our convolution 1 star beta, and we can forget about this because we have q equal to 1, okay? And well, unfortunately I don't have time to go into much detail about this, but here we can use Cauchy-Schwarz to separate these 1 and beta, and the point is that we will need to save something in both of them or get a good bound for both of them, and for the term with beta we can just use the mean value theorem, and for the term with 1, so there is some stuff going on, and what we end up is that this is okay if we can do this integration in a short range for this one function here, m of size m, 1 over m2 half plus it squared dt, and if we can get for this the correct bound, that this is go h1 1 plus epsilon, and if we had the second mode for all t, so what happens, we use Cauchy-Schwarz and we take a supremum over this t's for this first term with the 1s, and we end up needing something like this. And if we had the second moment of zeta for the short interval of length h1, we would be happy, but we don't. But then we can use, the point is that we have smaller m than what we would get from the approximate functional equation for the zeta, so we can write this as an exponential sum, and we get the saving from the Van-Der output for this thing here. So let me write one more line here. So if we smooth, we get that this left hand side is at most h over m times the sum of h smaller than m over h and sum of m of size m, and 1 plus h over m times it, and we get that this is smaller than h, and 1 plus epsilon by exponent there. So unfortunately I'm running out of time, and I didn't have much time to give details about this, but if you are somewhat familiar with these things, perhaps you can see that this will lead to a sum like this, and that you can use Van-Der output for doing bounding this, and you will end up with a bound like this if h is at least x to 2 over 7. And in order to go beyond to smaller exponents went over 7, I was claiming something like 8 over 33, I think, which is a bit smaller 1 over 4th. We have to be more careful here, and we can't just take the supremum, but we have to really use the averaging over D and prove some large value estimates, which becomes more difficult. But let me stop here. Thank you. So I think the result on the very short intervals can't say anything about the higher moments of theta, but the result on the longer intervals might say something in some short moments of theta or something like this, but we haven't figured it out yet, but we will take a look at it. So I don't remember very well. Do you remember? Well, at least x to epsilon, but I think something better. No, and some log x to something, I think. Probably, but I'm not sure.
Okay, so thank you very much to the organizers. It's a great pleasure to be back in MSRI. Yeah, so let me tell you a little bit about some problems that I've been thinking about for the last couple of years that are now starting to, well, we'll see. We'll see what they're starting to do. But it's generally studying questions about the interplay between geometry and arithmetic from the point of view of sphere packing. So let me go back to this thing that too many of you have heard me talk too much about. There's going to be one quick slide for any newbies. So there's Apollonius, and the Apollonian problem is given 3 circles. This is a special case where the 3 circles are already mutually tangent, to construct 2 further circles, or a single further circle that's tangent to all 3 of them. And we don't know Apollonius' solution. There was a solution using, of course, straight edge and compass by Viet around 1600. And actually, recently, Arthur Barragar and I found a construction that uses only 7 elementary moves of the straight edge and compass, which, if you really want at the end, I'll show you. Okay, so that's the Apollonian problem. Once you do that, so Leibniz is the first to have the idea to iterate this. So this is the dynamics of the Apollonian operation. And when you iterate it ad infinitum, you get what's called an Apollonian circle packing. And so the asymptotic growth rate of these circles was studied by O and myself a long time ago. And then the arithmetic comes in from a study by Frederick Soddy in the 1930s. Somehow everybody else missed this before Soddy. But he says, let's look at the, for circles it's curvatures, but in general we want to look at the reciprocals of the radii, so let's call those bends. For spheres, the curvature is proportional to radius squared, reciprocal of radius squared. So if we have a configuration where the first circles have curvature or bend 18, 23, and, well, this outer circle has radius 1/10, but we want the orientation to be opposite because it's internally tangent, so we'll call that -10. When we do this first operation, this straight edge and compass move with 7 elementary moves, the next circles will have radius 1 over 35 and 1 over 27, and more come in, and it turns out that they're all integers. So that's the story of integer Apollonian circle packings. And of course, the next question you should ask is, what integers arise? And that's something that many people worked on, including work of Bergan and myself, to prove almost local global principle in this setting. Okay, so that's all very old news. I'm not going to say anything more about that. But the question I became interested in is, okay, there are all these kind of miracles. Why do these things exist? That's kind of the question I wanted to try to understand. So how does the geometry of the Apollonian construction lead to the arithmetic discovered by Soddy? So let's look at this again. So the geometry and the dynamics, well, the packing is generated by dual circles, by reflections through dual circles. So what do I mean by that? Let's take C1, C2, and C3 as our initial 3 circles. They have 3 points of tangency. Those 3 points determine a circle. Let's call that circle C4 dual. And then the observation is that if you reflect the image through C4 dual, it fixes C1, C2, and C3, but sends C4 to C4 prime, the other solution to the Apollonian problem. So these two are dual to one another. And so if you look at C1, C2, C3, and C4, now you have a number of dual circles, in fact 4. And if you take the group generated by reflections through those 4 circles and you start moving the initial circles, you get the entire package. And the key idea here, if you want to study this operation, the dynamics, the idea of Poincare is to give yourself some complex analysis, move away from the plane into the upper half space. So think of this group not as acting in the plane, but as acting in hyperbolic space, so as a reflection group of isometries. So then the picture you see, I don't know if you can see this in the back, but it's the same circles, C1, C2, C3, 4, dual. So these are the dual circles. And what's being shown here is an orbit of a single point in upper half space under reflection. So the reflection through C4 brings it here, and then reflection through C2 there, and so on. And I hope you can see that the limit set of this hyperbolic reflection group is this Apollonian circle packing. So that's another way to realize this object. And that's very important for studying both the dynamics and the arithmetic properties. And where does the arithmetic come from? Well, it comes from an old theorem of Descartes that if you have 4 mutually tangent circles with bends B1 through B4, then they satisfy this nice algebraic relation. And although Descartes proved this, and many people followed Descartes and understood his proof and appreciated it, somehow none of them took the next step until Soddy, which is if you have B1, B2, and B3, then you have a quadratic equation in B4. So there are 2 solutions. Those are the 2 possible circles to place there, and one is related to the other by an integer linear combination of the previous curvatures. So it turns out that so that's where the integrality is coming from. If the initial 4 tangent circles have all integer bends, then forever you'll have integer bends because the bends are integer linear combinations of previous. Okay, so that's what's going on in the Apollonian packing. So what's happening more generally? So there were a lot of other, well, not a lot, a handful of other examples. For example, Soddy already studied the sphere packing, the integer sphere packing, which I call the Soddy packing. And I studied the local global problem in this context. So today we would call this the 4-simplex. I'll explain where this terminology is coming from. There's a very old paper of Boyd's in '74, which I only recently discovered has a construction that until now I'd been attributing to Göttler-Mallows. And this is what my student Xin Zhang worked on for his thesis, proving the analog of my theorem with Bergan, this almost local global theorem for these packings. And then the analog of the Soddy theorem was worked out by Diaz and Nakamura for the 4 orthoplex. So there's some other sphere packings, and there are a few other examples, notably by Kate Stange and others by Arthur Barragar and others. So what's the setting? What's the game I want to play? So I will call a packing of Rn. A packing is a collection, infinite collection of n-1 spheres. I will want them oriented. So there's a direction, which way will we call inside? And of course, limits of spheres are okay, so that's planes, hyperplanes. And I will want it to be a packing, so the interiors of the spheres should be disjoint. And again, I will want it to be a packing, which to me says that the tangency graph is connected. Okay, so the spheres are touching each other. And I will want it to be a packing. I want it to fill up all of space. So if you take the interiors of all the spheres, and you take the union of those, and the closure should be all of space. Okay, so there's no ball missing from space that's not intersecting at least some sphere. Okay, so this is again unequal packing of spheres, not to be confused with the recent work on E8 and 24 dimensional. So this is, you see the picture. Okay, so that's what a packing is. Now, as stated, there's no structure. Right? You just arbitrarily make your favorite collection of spheres that just touch, and some, you know, wherever you have space, you stick another sphere in, and there's a packing. So we need some structure to study this. And the structure I will want is the one that we have for the Apollonian group, namely hyperbolic reflection group. So I will say a gamma packing is a packing which arises as the limit set of some geometrically finite hyperbolic reflection group. So this is a group acting on isometries on hyperbolic n+1 space, as we had, if you saw the initial picture. So we have circles in the plane, and you'll very quickly see why I need the computer to draw pictures for me. We have circles in the plane, and the right thing to think of, so this is Rn, and the circles or spheres are Sn-1s, but the action is actually taking place in hyperbolic n+1 space. Okay, so that's this inversion through these spheres. Okay, so is that clear? Any questions on the game that I want to play? So this is what I want a gamma packing to be. Geometrically, what you're really giving me is not just the packing, but you're also giving me a symmetry group gamma, which of course will fix the packing since it's geometrically finite, it's automatically finitely generated. I haven't specified that it's Zariski dense in the definition, but actually it has to be Zariski dense for the packing to fill up all of space. Any other questions? Okay. So of course the problem then is to classify integral gamma packings. Or so I thought. And it turns out that's not the right problem. And I'll explain why. So I have to explain the notion of superintegrality. So what is a supergroup? Let me explain. So what you do is someone gives you a gamma packing. That means you have the packing and the group acting on it. So the supergroup is the group which is generated by the original group and also inversions through all the spheres in the packing itself. So let's just see an example of that. Here's an Apollonian packing, a strip packing, and the group is the group generated by these four reflections. That's gamma. What's gamma twiddle? Gamma twiddle is the group generated by all the reflections of all these circles, and it turns out